All right, hello everybody, welcome back. One of the questions at the end of class on Monday was to give a more concrete example of stochastic gradient descent, which is a great idea. So I posted a movie and some code to Piazza, and we're going to take a look at the movie and the code to start off this class. So first, let's take a look at the movie. So I'll go ahead and play it. So what's happening here, we have a bunch of samples, which are the x's, and the samples, we're going to assume that they're from a Gaussian distribution, and in fact they are. I generated them myself. So it's a 2D Gaussian distribution. We'll talk a lot more about the Gaussian distribution later, but for now, here's a bunch of samples from it. And what we're going to do is we're going to try and fit the mean and the variance of that distribution using stochastic gradient descent. So I should say right off the bat, stochastic gradient descent is not actually the best algorithm to use in this situation because it's really fast to calculate the batch maximum, the global optimum of the likelihood function. But we'll use it as an example anyway because it shows sort of how the algorithm works. And so what we're going to do is we're going to estimate the parameters, the mean and the variance, using maximum likelihood. So that means that our objective function that we're trying to minimize is the negative of the log likelihood, right? So the likelihood is the probability of the data given our current guess of the parameters. So that's a number, the probability of the data. So a single real output, and the inputs are the parameters, in this case the mean and the variance matrix. And to maximize that, it's equivalent to maximize the log of that because the log is a monotone function, and it's equivalent then to minimize the negative of the log. And that's the way we usually set it up because so far we've been talking about gradient descent as a way to minimize functions. There's also gradient ascent, which is for maximizing functions, but there's no reason to switch to that. All right, so so the x's are our samples. The black ellipse here represents the ground truth distribution. In other words, I generated this data from a normal distribution, and that normal distribution has a mean, which is here at the center of the ellipse, and it has a variance matrix, and the way the variance matrix is set up is so that the variance is largest along the major axis of this ellipse and smallest along the minor axis of the ellipse. And I've set up the ellipse so that its size is proportional to the standard deviation in any given direction. So the ellipse represents our Gaussian distribution. We can compute the batch maximum likelihood estimate, in other words, the global optimum of the function we're trying to minimize, and that's this blue ellipse, and it's not the same as the black one, but it's fairly close. And so you can see here we're representing parameters for the Gaussian distribution by these ellipses, because that's a good way to visualize them. It shows both the mean and the variance, right? So natively the mean is a vector of length 2, it's a position in the plane, and the variance is a 2 by 2 matrix. And to visualize those, we can just use this ellipse. And then when we run stochastic gradient descent, I've initialized it to something over here, right, which is in the wrong spot. And every step of stochastic gradient descent, right, I'll run it again here. Every step of stochastic gradient descent, we're going to sample a mini batch. In this case, I think I used 10 examples, so 10 of these x's. And we're going to compute the gradients based on that mini batch and update the mean and the variance by subtracting a multiple of those gradients. All right, so as always, please ask questions on Piazza. And I'm going to switch now to, let's play this once more for good measure, and then I will switch to looking at the derivation of the corresponding gradient descent update. All right. So actually, let's look first at the code, right? So this code is available on Piazza. It's in MATLAB, so you can, the school provides MATLAB licenses. You can download MATLAB and use it to run this code, or you can just read the code and watch the movie. That might be the recommended option, unless you want to change something and play with it. So here are the true mean and true variance, a vector and a matrix. I generated 75 points, and the way I generated them is to take a random normal matrix, so that's 2 by n, so each column represents a single point. I multiply by the square root of the variance matrix. Again, this is something that we discussed in the first mini, so there are notes on it if you want to go back and look at it. And then I add in the mean, right? So MATLAB's BSX Fun, it's a really weird name, but all it does is it does broadcasting. So if you want to add a vector to every column of a matrix, you use BSX Fun. All right, so the batch maximum likelihood estimate is simple to compute in this case. The mean is the mean of all of your training points, and the variance is you take each point and you subtract your estimated mean, and then you take the empirical variance, right? Meaning the sum over all training examples of that training example outer product with itself divided by the number of training examples. All right, so here we initialize to mean zero and identity covariance matrix. We set up the plot that you guys were watching in the movie, and then we run stochastic gradient. So in stochastic gradient, we have to choose a learning rate, which I chose to be 0.1, a mini batch size, which I chose to be 10, and a number of iterations to run for, which I chose to be 150. In each mini batch, we take, in this case, I used without replacement sampling, so I take a sample of 10 distinct training points and just store them in batch x's. And then here, you don't need to understand these formulas yet because we haven't derived them, but you calculate the gradient of the likelihood with respect to mu and the gradient of the likelihood with respect to variance, and you update mean and variance. And the way you do that is you subtract the learning rate times the gradient from each one of them. All right. And then we update the plot and write out a frame of the movie. So hopefully that code makes sense. And now let us so somebody is asking about how to choose a better loss function, right? So in this case, we chose negative log likelihood. And the question actually suggests another option, which is cross-entropy loss. It turns out that cross-entropy loss is, in fact, negative log likelihood. So there's no need to choose between the two. What you're choosing is a way to set up the problem. So in particular, cross-entropy, what we're doing is we're assuming that so cross-entropy is for a classification problem, and we're assuming so the classification problem, your data. So here, right, for our normal example, right, we observe a whole bunch of samples xt, each of which is distributed as a normal distribution with mean mu and variance matrix. I guess I called it V in the code, right? So that's the movie. You could also have a bunch of samples, xt, yt, where these are distributed as some arbitrary distribution over xt times a conditional distribution for yt given xt, which is Bernoulli, with probability well, let's say we're using logistic regression, right? So logistic regression would have the probability be the sigmoid function applied to w dot xt, right? So here, right, the Bernoulli distribution here is the conditional distribution of y given x, and here we're picking an arbitrary distribution for x. And if we now do maximum likelihood on this representation, so we're not fitting p of xt, we just assume it's arbitrary, and we're fitting p of yt given xt, that is in fact identical to cross entropy loss. So maximum likelihood is a very general thing, and cross entropy is a special case of it. So somebody's asking now about mini batches. So you can see exactly in the code how we treat the mini batches. But the question is whether we are using the same mini batch over and over, and the answer is no. You select a separate mini batch on every iteration of stochastic gradient. And if we iterate for a large number of times, are we eventually going to use all the training data? Yes, if we just keep selecting random mini batches, eventually you're going to just randomly happen to hit every example in your training data. And so it's important that you're selecting these mini batches uniformly at random, because that means that you do have a positive probability of seeing any training example. And so that means since you have a positive probability of seeing any training example, you'll see all of them eventually. And if you didn't, right, if you excluded some training examples from your mini batches or something like that, you would have potentially a biased estimate in the end. And so that would be a bad idea. All right, so that's the code and the movie. Let us take a look. Okay, so I updated the notes from Monday because it seemed to make most sense there. I just put the example at the end of the notes from Monday. So if you reload those notes, you can see there's a new 12th section. And so here what we're doing is we're just deriving, we're spelling out the situation in detail, and we're deriving the stochastic gradient descent updates. So I said before, a 2D Gaussian distribution, mean mu, variance, I guess I called it sigma here instead of v. We have a batch of t observations from that distribution. And we want to fit mu and sigma by minimizing the negative log likelihood, right? And the negative log likelihood has this sum of terms form that we've been talking about. It's the sum over training examples of the likelihood term that corresponds to that training example. And here's that likelihood term for the Gaussian distribution. There's no reason you should know this form. And in fact, I always wind up looking it up on Wikipedia just to make sure that I get the sign of each one of the terms correct. And to make sure I get the constants correct and all of that sort of thing. But here it is, right? So half of the log determinant of sigma plus a quadratic form that involves sigma inverse and xt minus mu. All right. So again, just mentioned that SGD is not the right algorithm for this situation in the real world, but it's still a good example, right? So it's actually turns out to be really fast to calculate the batch maximum likelihood. You saw there was code for it in the code file. All right, so to run stochastic gradient descent, we need to take the gradient of each loss term with respect to mu and sigma. Right, and so this is something that we practiced a lot in the first mini, and all of the tools from matrix differential calculus that we talked about there are going to be really useful, and we're gonna use them. So the mean is simpler, right? So we can, let's see. So here's the likelihood term, right? So let's just do that, do the gradient. So we would like to get dLt of mu, sigma and now we're differentiating with respect to mu and considering sigma a constant. So when we go through, when we differentiate this term, there's no mu in it, right? So this term, the sigma term, the log determinant sigma term just drops. And so we have d of, and let's expand out the square. So that's, also there's a half out in front, d of x t transpose sigma inverse x t minus 2x t transpose sigma inverse mu plus mu transpose mu, right? So so here in the middle, right, this is just expanding out the square, but here in the middle I've collected the two terms, right? There's xt transpose sigma inverse mu and a mu transpose sigma inverse xt, and those two terms are the same, right, because a scalar is its own transpose. And so I've just collected them. All right, so then this first term also doesn't contain mu, so we ignore it. So we can just go through now and have a half. Here, right, we take the derivative, so we get minus 2xt transpose sigma inverse d mu. And then here we have to use the product rule, right? This is plus mu transpose d mu plus d mu transpose mu, right? All right, and so collecting terms, right, we get, so the half and the 2 cancel, minus xt transpose sigma inverse d mu. And then again, a scalar is its own transpose, right? So both of these terms, mu transpose d mu and d mu transpose mu, those are both scalars, and so they're actually equal to each other. So there's 2 of them, the 2 cancels with the half, and so we'll get plus mu transpose d mu. All right, and that is equivalent to what I just wrote here in the notes. And then the gradient, right, is the coefficient of d mu in this expression, right? So it's just transposing it to get a column vector. It's sigma inverse mu minus sigma inverse xt, which is this thing here. Okay, so by this time you guys should find the that sort of differentiation effortless. I've gone through it in some detail. If you have questions about it, please post, and if you and if it's not effortless for you to do a derivative like this, I would recommend doing some more practice on differentiation, maybe using some of the examples that are in the lecture notes from First Mini. All right, so same thing, we can do the same thing for the derivative with respect to sigma, right? This one is a little bit more complicated, but we can still do it, right? So with respect to sigma, we have dLt of mu sigma is equal to, right? And so the first thing is that we have to differentiate the log determinant of sigma. And it turns out that there's an identity for that. We mentioned it briefly in the first mini. You don't, if you don't happen to remember that, then you would just look it up in a table of identities. And so we get 1/2 sigma inverse d sigma, right? That's the trace of sigma inverse d sigma. That's the identity for the differential of log determinant. And then the second term, right, this term right here, that's actually, we can write it out like this, 1/2 x t minus mu, it's an x, transpose d of sigma inverse x t minus mu, right? And then we would use so this was just by linearity, right? You can just pull constants outside of the differential, and mu is a constant right now because we're differentiating with respect to sigma. And then you use the identity for the differential of a matrix inverse, which again we mentioned briefly in first mini, but you would, if you don't happen to remember it, look it up in a table of identities, and that is just sigma inverse d sigma sigma inverse. All right. So that gets us the first line down here, right? That's this expression right here is exactly this expression here. And then to get this second line, right? So why are we not done? I mean, we've computed the differential, but what we would like to do is get the gradient, and the gradient is the coefficient of d sigma in the differential. All right, I thought I had all of my notifications turned off, but apparently Microsoft would love to interrupt class. Thank you, Microsoft. All right, so so we would like to set it up so that there's a coefficient of d sigma that we can use as a gradient, and so that's what this second line is doing. And so here in this first term we're good. There's a coefficient of d sigma. Here what we want to do, all right, so this whole expression represents a scalar, so it's equal to its own trace, right? So this is equal to 1/2 trace of sigma inverse d sigma plus 1/2 trace of all of that stuff. And then we can use trace rotation. So trace rotation, again, is an identity that we covered in the first mini. It is extraordinarily useful, and a lot of people don't know about it, so it's worth remembering. But what trace rotation says is that if you have a matrix product, trace of ABC, you can just rotate that matrix product as much as you want. So trace of CAB or BCA, right? Those are all the same thing. Yeah, so that's the trace rotation identity. And so what we're going to do, we have the trace of this second term right here. What we're going to do is rotate, right? Rotate so that d sigma is last. So that means that we're going to take this part, the sigma inverse xt minus mu, and rotate it to the front. And so that is sigma inverse xt minus mu, and then this part here, which is xt minus mu transpose sigma inverse d sigma, and that is the second line of this derivation here. So that's how we. So we've just calculated the two gradients, right? And so we can pull out the coefficient of d sigma here, which is sigma inverse plus this outer product of two vectors, right, or outer product of a vector with itself. No reason, like this functional form is not something that you would remember, but you can calculate it very easily if you need to. And then stochastic gradient descent, it works the way the code shows, which is you repeatedly pick a mini batch. So this is the gradient with respect to one example. The gradient for a mini batch is just the average of this over all of the samples in the mini batch. And so we repeatedly pick a mini batch, compute the gradient of each example, average over all examples in the mini batch, and use that to update our mean and variance. All right, so that is the example. Hopefully it's helpful. And just because movies are fun, let's watch it one more time now that we know everything that's going on, right? And again, you can download this movie from from Piazza. And so you can, and the code as well. All right, so oh, why is the gradient the coefficient of d mu? That is, it's called an identification theorem for matrix differential calculus. In the toward the end of the first mini, we had so matrix differential calculus. It is typically the fastest, at least once you've practiced it, and definitely the most general way of calculating derivatives. And it includes, as special cases, a lot of the notions of derivative that you may have seen in previous courses. So it includes gradients, it includes Jacobians, it includes tangents, right? All of these specific types of derivatives. And so there's a table in the lecture notes towards the end of the first mini that shows how these match up. Like what does a gradient look like in matrix differential notation, or what does a Jacobian look like in matrix differential notation? And it turns out that for a gradient, what it is that the gradient transpose times the differential of x is going to be the matrix differential. And so you can just, if you calculate the matrix differential, you read off the gradient. What is the reason that we want differentials with respect to the mean and variance? So again, the goal of this entire exercise is to implement stochastic gradient descent. So we need to calculate the gradient of the function we're trying to minimize. And so to calculate that gradient, we compute the differential with respect to mu and the differential with respect to sigma, and we read off the gradient as the coefficient of mu or sigma in that differential. So in general, the way SGD works, right, we'll start with a function that we want to minimize. So in this case, that's the negative log likelihood of a Gaussian distribution. And that function is a sum of terms. And the way stochastic gradient descent works is we take a random mini batch, a subset of our terms, and calculate the gradient of those terms with respect to our parameters, mu and sigma, and then update our parameters in the direction of the negative gradient, right? And so the reason we need to calculate the differential is to get the gradient so that we can run stochastic gradient descent. All right, so let's move on to the next topic in the lecture notes, and feel free to keep asking questions on either the old or the new topic on Piazza. All right, so at the beginning of the course, we talked about using discrete probability distributions to model the world. So coin flips or die rolls or draws of a card from a deck. A lot of times we would actually like to model a continuous variable instead. And so we'll talk soon about continuous probability distributions. But before we get there, I wanted to take a detour and talk about what probability means for a continuous random variable, because it's actually not as straightforward as one might immediately think. So a good example of a continuous random variable is we take a measurement of the distance from New York to LA and report it back, right? And that can be, in theory, our measurement could be any real number, right? I mean, some of them are more likely than others. We're not very likely to measure 1 inch as the distance from New York to LA, but in theory, it could be any real number. And so the first thing is that we can make this measurement discrete by discretizing it, right? Like we can say, okay, I'm going to just assume that I'm going to measure an integer number of microns. And if I don't, I'm going to round to the nearest micron, and that's going to be my answer. And so I could measure something like 4.5 times 10 to the 12 microns from New York to LA, which actually is fairly close to the truth. And that's an unimaginably large number because we were foolish enough to measure the distance from New York to LA in microns, but it is a discrete random variable, and so all of the stuff we've done about probability distributions, conditioning, Bayes rule, sum rule, all of these things, they all work directly on the discrete random variable. And so you would never do that in practice because it's really unwieldy to work with with discrete measurements like that. But for intuition, that's what you should be falling back on, right? Just think of it as a discrete number of microns and you'll be good. And the reason it's really inconvenient is that let's imagine that we had a probability table for this measurement, and it's going to have, 10 to the 13 entries in that probability table, which is just ridiculous to have to deal with. Or let's suppose we had a joint probability for 2 such measurements, right? Then it would have 10 to the 13 squared or 10 to the 26 entries in that joint probability table. And there's just no way that you're going to store that on your computer, right? It's just, and certainly no way you're going to iterate over it to do conditioning or anything like that. All right, so what do we do instead? We work with oh, yes, somebody pointed out an error in where I just forgot a term here. So that is an excellent point. We'll just move over that d mu and put in the sigma inverse that's supposed to be there. Sigma inverse. There we go. Sorry about that. Thank you for pointing that out. Now the lecture notes are going to be consistent with what I wrote on the slides. All right, so what are we going to do instead? We're instead of doing the discretization thing. So what we're going to do is we're going to work with probability density instead of probability. So what is a probability density? So for a discrete random variable, it makes sense to ask for the probability of a single outcome, right? So like, what is the probability that we measure exactly 4.5 times 10 to the 12 microns as our distance from New York to LA? And it turns out that probability is going to be fairly small, right? Like the chance that we exactly hit that many microns in our measurement is not so big. But it's going to be positive, not 0. By contrast, when we have a continuous random variable, for all or almost all of the values that variable can take, we're going to have precisely 0 probability of hitting that measurement, right? There's the chance of hitting exactly pi when you choose a random number uniformly in 1 to 10 is not just small, it's 0. And since these probabilities are small, it doesn't make are 0 instead of being small, it doesn't make sense to add them up, right? If you ask for the probability that x is between 3 and 4, right? For a discrete random variable, you just add up the probabilities of every event that's between 3 and 4. But for a continuous random variable, if you tried to do that, every event would have 0 probability and there'd be infinitely many of them, so you'd get 0 times infinity, which is not a number. And so that's not obviously going to be the right way to do it. And so what we're going to do instead is we're going to work with a different quantity, which is called a probability density. And a probability density is effectively the derivative of a probability, and that doesn't make sense right now, but it hopefully will in a few paragraphs. All right, so what is a density? Somebody's asking on Piazza about the log determinant. Where did that come from? That comes from the expression for a Gaussian distribution. If you just look up on Wikipedia, the expression for a Gaussian distribution, for the likelihood for a Gaussian distribution, you will find that there's a determinant in the likelihood, and therefore a log determinant in the log likelihood. So the answer for where did it come from is it came from where we looked it up. All right, so what is a density? A density is for a real valued random variable, let's say x, and suppose that there's some function little f of x, such that if we integrate that function over an interval, like 3 to 4 or 0 to 1, we'll get the probability that x falls in that interval. Okay? So if that's true, then that little function, if that's true for every possible interval, then that function little f of x is called the density for x. So for example, for a Gaussian distribution, this is a univariate Gaussian distribution. The density is this expression that we gave here, 1 over the square root of 2 pi times e to the minus x squared over 2. So that's a Gaussian distribution, with a univariate Gaussian distribution with mean 0 and variance 1. And so what that means is that for any interval like 0, 1, if we integrate from 0 to 1 this density, we will get the probability that x is between 0 and 1 if we sample it from a normal distribution. Okay, so that's the definition of a density. We can relate that to probability the following way. So we can, if we want a non-zero probability, we can ask for the probability that our continuous random variable is in some interval. And so specifically, if we take the interval from minus infinity to little x, that will give us the probability that big X is less than or equal to little x. And if we have that for every possible value of little x, that's called the cumulative distribution function, or the CDF, of our random variable, right? And so that actually turns out completely describes the distribution of our random variable. And it looks like this, right? So here is, for a Gaussian distribution, 50% of the time we're less than or equal to 0. About 5% of the time, about 2.5% of the time we're less than or equal to minus 2, right? And about a sixth of the time we're less than or equal to minus 1. So this is what it looks like. So the CDF is always monotone. It always starts at 0 at the limit as you go to minus infinity, and it increases or stays the same as you go over towards plus infinity, and it limits to plus 1 at plus infinity. So if you look at the definition of CDF, and if you look at the definition of density, right, the fundamental theorem of calculus tells you the relationship between the two of them, right? So integral is antiderivative. That's the fundamental theorem of calculus. And so in particular, the derivative of the CDF is the same as the density. So density is the derivative of probability. So in particular, density is not probability. It is the derivative of probability, which is a related thing, but not the same, right? And so in differential notation, right, the differential of the cumulative distribution function is the density function times the differential of x. And that's, in fact, just exactly the chain rule that tells you that this f of x has to be capital F prime of x. Right? And so we can, instead of having integral of f of x dx, we can also, and you will sometimes see this, write the integral df of x, d capital F of x, where capital F refers to the cumulative distribution function instead of a density directly. All right, so that's a density and a cumulative distribution function, and they're related to one another. And when we work with a continuous random variable, we're typically going to work with its density. That winds up being the thing which is most similar to working with a probability. Okay, so there's a question about how to set the learning rate for stochastic gradient descent. So there's in the lecture notes from last time around, there's a bunch of practical tips for setting the learning rate. There's not, in general, a theoretical result that says what's going to work. We know that if we set it small enough, it will always work, but if we set it too small, it's going to run really slowly. And so what we want to do is sort of set it big, and if it doesn't seem to be working, decrease it. And if it doesn't seem to be working, decrease it. And that's sort of the theoretically motivated way to set the learning rate. You start with an overestimate and you decrease it until it starts to actually work, to converge. Of course, for practice, there's people use sort of experience and heuristics to guess what a good learning rate to start out with is. And I don't know, it's more just like experience with your data set and experience with your loss function that let you guess what a good learning rate is for your situation. All right, so I almost hate to have to point this out, but there is a notation confusion that results from people using the same notation for two different things. So if we have f of x, which is a density, not a probability, it's actually common to write p of x for the density of the random variable x. And so that is a conflict because density and probability are two different things. It's not a bad conflict because in most cases you know which of those two things you're dealing with. You know whether your variable is continuous or discrete, and so that's why the notation conflict persists. If we were being careful, we would write something more like this line here, right? We would have capital P for probability, and the probability would be of an event like capital X less than some cutoff little x, and then we would say define little p to be the density and distinguish the density from the probability by using capital versus lowercase letters or some other convention, right? But again, people will often conflate the two of them and use the same notation to mean probability or density, depending on whether the variable is discrete or continuous. It's just a public service announcement to point this out because you can get very confused if you mistake one for the other, right? So for example, if you think something is a probability and it's in fact a density, probabilities are all less than or equal to 1, and densities can be bigger than 1 as long as they aren't bigger for such a big region that it integrates to more than 1. And so they have different properties, and you can be confused by which properties you expect if you don't know what the correct interpretation is. All right, so just like probabilities, there are conditional densities, right? So if we have a function capital F, which is the cumulative distribution function for a random variable x, in its distribution conditional on seeing a value for a random variable y, right? Its differential with respect to x will be this, and this is a conditional density, right? It's a function both of the place where you condition on, y, and the value you're asking about for the random variable x. But it's only a distribution with respect, it's only a density with respect to its first argument, right? A conditional density is not a density with respect to its second argument. Meaning, for example, that if you integrate over the first argument over its entire range, you'll get 1. If you integrate over the second argument, you'll get something meaningless. And so that is basically how we deal with continuous random variables. In most cases, we'll wind up being able to use the density in the same places that we use the probability. So in particular, maximum likelihood works with continuous observations as well. And all that you have to do is say that the likelihood in the continuous case is equal to the density of your observation given your parameters, as opposed to the probability of your observation given the parameters. And everything else goes through just like it did for a maximum likelihood with a discrete observation. All right, and then the last thing to mention is just a caution, which is that there's a lot of paradoxes that happen if you are not careful with how you deal with densities. So in particular, when you're working with densities, you should worry about whether the integrals that you're taking converge, right? Meaning whether they have a defined value. should worry about whether it's okay to exchange differentiation and integration, right? So you can always move differentiation through a sum, but you can only move differentiation through an integral if certain, quote, regularity conditions hold. And they will always in this course, but in general, you can get yourself into trouble by forgetting to check these regularity conditions. And coordinate systems make a big difference as well. So, for example, if you have a random variable that takes values on the surface of a sphere, you could have a coordinate system which is like latitude and longitude, right? Or you could have a coordinate system which is like the projective plane, or you could have a coordinate system which is like latitude and longitude but with the poles moved to a different spot on the sphere, right? And all of these different coordinate systems, they affect how integrals are computed. And if you're doing your reasoning correctly, then you will get the same answer in each one of these coordinate systems. But it's very easy not to do reasoning correctly and to forget to compensate for a change of coordinates when you're moving from one coordinate system to the other. And there are ways to handle all of these problems. And the general term for these ways is called measure theory. And you can take an entire semester-long course on measure theory from the stats department. It is an excellent course, and so I recommend it if you're interested in these sorts of things. Or if you're not interested in these sorts of things, I recommend just being careful when you sail off the edges of the map, right? Like always think about what's the equivalent result that you would get if you discretized, and think about what's an appropriate discretization and make sure that it all makes sense with multiple different discretizations. All right. So just checking. All right, so there. I think I've answered all of the questions on Piazza. So I think it makes sense to move to the next set of lecture notes. All right, so we talked about a week ago about how to model the world using discrete random variables. And now that we know what a density is, it makes sense to ask how to model the world using continuous random variables. And so first, we're going to talk about a bunch of common situations that you might encounter and what are the appropriate probability distributions to handle these situations. And then we're going to talk about sort of more general tools for how do you handle, how do you roll your own distribution to handle a new situation. And again, this is for single continuous random variables only at the moment, and after we're done with this, we're going to talk about how to handle multiple random variables at once. All right, so there's a few common situations, uniform, normal, and beta, which we'll talk about, and then we'll talk about how to, and power law is a fairly general common situation. We'll talk about that as well. But we'll also talk about how to make up your own distribution if you need to model something that doesn't fit one of the common families. All right, so uniform distribution, simple enough that we won't spend a lot of time on it. Basically, equal probability of falling anywhere in some interval. And so the parameters are the ends of the interval, and the density is just constant within the interval, so that the probability of falling in any subinterval is proportional to the length of that subinterval. Right? All right, then the big case is the normal distribution, right? This is maybe the single most commonly used distribution ever, and there are good reasons for that we'll mention. But the normal distribution has a density that looks like this, right? It's the famous bell curve, where you have a high probability of being near the mean, which is in this case 0, and then probability that falls off gently as you go larger, and gets extremely small, like it's effectively 0 once you get beyond plus or minus 4. And so why is it so common? One is that it's analytically tractable. It's really easy to work with in a lot of situations, and so people like that. That's not, of course, a good reason to use it to model reality. There's no reason that reality should be analytically tractable. But it turns out that reality is, in many cases, well modeled by a Gaussian distribution. And in particular, there's this thing called the central limit theorem that says that there's a very common situation where Gaussians are a near perfect model. So the central limit theorem says that if we take a whole bunch of random variables, no one of which is too large, and if we take the sum or the average of these random variables, then that sum or average is going to have very close to a Gaussian distribution. And it's going to get closer the more random variables you take, but in fact, it's a limiting result, hence the name central limit theorem, but it turns out already to be true for fairly small numbers of random variables. So a sum of like 30 coin flips or 50 is already quite close to being normally distributed. Right. So one of the reasons that normal distributions are analytically tractable is that they're closed under addition and scalar multiplication, meaning if you add together two normal distributions, you get a normal distribution, and if you add together two random variables, each of which follows a normal distribution, their sum is another random variable which also follows a normal distribution. Same thing with scalar multiples. So if the random variable x is normally distributed, then so is 3x, so is 5x, and so forth. Normal has two parameters, mean and variance. The square root of the variance is called the standard deviation. Mean takes your distribution and shifts it left to right, and variance scales it wider or narrower. The density looks like this. Again, I remember it because I see it all the time, but if you forget it, you can always look it up on Wikipedia or in the back of your favorite stats textbook. Couple of useful rules of thumb for dealing with the normal distribution. If you want to know what are likely values of x, if x is normally distributed, about 2/3 of the time x is going to fall between minus sigma and sigma, meaning plus or minus 1 standard deviation, and about 95% of the time it'll fall between plus and minus 2 sigma. All right, so here's an illustration of the central limit theorem, right? So what I'm showing here are two different cumulative distribution functions. One is the red one, the smooth one, is the CDF of a normal distribution, and the other one is the CDF of 50 coin flips, the mean of 50 coin flips. And so you can see, let's see, so the coin actually has means something like 0.3, right? You can read off the center of this distribution from the plot. And so we flip a biased coin 50 times, and we take the total number of heads and divide it by 50, right? That's the random variable. And that random variable, its CDF is in blue, and it's a step function because we can only ever observe, right, it's a staircase function because we can only ever observe an integer number of heads. But already, even with just 50 here, we're quite close to following a normal distribution. And as the number of coin flips gets larger, it becomes harder and harder to see the staircases, and it will effectively converge to being a normal distribution. So that's coin flips, right, our favorite synthetic example, but maybe a more real-world example is that height and weight and a whole bunch of other physical measurements on a person are determined by genetic and environmental factors, and there's only a few such factors that have an individually significant effect, right? Like, for example, your gender has a significant effect on your expected height. And so if you condition on the individually significant factors, and then look at the distribution of people's heights conditioned on those factors, they will be the sum of a whole bunch of individually insignificant effects, and so they'll be very well modeled by a normal distribution. And if you look at population tables, they are in fact extremely close to normal. All right, so the next distribution I want to talk about is the beta distribution. So for discrete random variables, we had the Bernoulli distribution, which was heads or tails, right? Like just two possible outcomes, what was the probability of one of the outcomes? And then the other outcome has probability 1 minus the first probability. But that probability, if you're trying to think of that probability itself as a random variable, right? So not the outcome of the coin flip, but the probability of the coin landing heads. That is a perfectly good random variable, right? Like you could imagine being handed a coin at random from a batch of weighted coins and you don't know what its p of heads is going to be. That's a perfectly good random variable. So you can model probabilities using the beta distribution, right? So the beta distribution, a sample from a beta distribution is a real number between 0 and 1 that you can interpret as a probability. And the density of the beta distribution looks like what's shown here, right? It's p to the alpha times 1 minus p to the beta, where alpha and beta are the parameters of the beta distribution. And then there's a normalizing constant that doesn't depend on p. And the reason that beta distributions work well for estimating probabilities is that they arise naturally if you're looking at the posterior, if you're trying to estimate a probability from counts. So let's say that you have a coin and you flipped it a bunch of times and you got alpha heads and beta tails, right? And you started with a uniform prior over your probability of heads. Then your posterior is going to be beta with parameters, the number of heads alpha and the number of tails beta, right? So the beta arises naturally if you start from a uniform distribution as your prior over the probability and then update it based on looking at some coin flips. And for that reason, the parameters of a beta distribution, you can think of them as virtual counts, right? So alpha is the number of heads you've observed and beta is the number of tails you've observed. Of course, you can have fractional ones. So unlike real counts, you can have a beta distribution with fractional parameters, and that's just fine. All right. So so if none of these pre-constructed distributions fits your case for a continuous random variable, there are a couple of different options. One is to empirically estimate a distribution, and the other is to use something like maxent or an exponential family to define a family of distributions that you're going to work with. So let's look at empirical estimates first. There's two kinds of empirical estimates that we're going to mention here. One is a piecewise linear CDF, cumulative distribution function, and the other is what's called a kernel density estimate. So let's look at piecewise linear CDFs. So the picture is really worth 1,000 words here, right? So let's just make that bigger. So what we have here is a true density in red, and then we took a bunch of samples from this true density, and we make an empirical estimate by sorting our samples and taking the smallest sample to start at density 0, And then for each new sample, we go up. So let's say there are 50 samples here. We'd go up by 1 over 50 to reach the second sample, and another 1 over 50 to reach the third sample, and another 1 over 50 to reach the fourth, and another, and another, and another, and so forth. Right? So here the x values are our samples that we took in sorted order, and the y values are just 0 for the first one. I guess, so if we had 50 of them, it would be 1 over 49 for the second one, 2 over 49 for the third one, all the way up to 49 over 49, which is equal to 1 for the last one, right? So that is, that's that. Here is the formula. It's kind of a mess, so you wouldn't want to look at the formula unless you needed it for some computation. But the procedure is up here, right? We sort our sample and assign each point a probability from 0 to 1 in increments of 1 over n minus 1, so that you assign the ith point the probability I minus 1 over n minus 1, and then you just connect those points with lines to make an estimated CDF. All right. Right, so in the beta distribution, somebody's asking what's the difference between the density of P and P itself, right? So both P of P and P itself are probabilities, right? But they're probabilities of different things. So imagine that we have the following experiment. We get a coin with an unknown weighting. So we don't know how often it'll come up heads or tails. And then we flip that coin once and observe whether it comes up heads or tails. So we can model that with a beta and a Bernoulli distribution, right? So the Bernoulli distribution tells us what's the probability of coming up heads, excuse me, and it has one parameter for the Bernoulli distribution, which is the probability of heads. But since we don't know the probability of heads, we have to have a distribution over it. And that distribution is the beta, right? So we have a probability distribution over the probability of heads. And so we have this formula here, the beta formula, which gives us the probability density over the P, which is the parameter of our Bernoulli distribution, right? So they're both probabilities, but they're probabilities of different things. And so it's a little bit confusing maybe to keep them straight, but it is important to keep them straight. Yeah. So all right. So that's piecewise linear CDFs. Just sort your points, assign each one a probability in even increments, and then connect the points with a line to make a CDF. The other thing that you can do is what's called a kernel density estimate. So the kernel density estimate starts from something called a kernel, which is, so I guess first I should say the word kernel is overused. So we used it in the first mini in relationship to function spaces and support vector machines and that sort of thing. This is not that kind of kernel, right? So in this context, a kernel is just a narrow probability distribution. So we could take like a Gaussian with a narrow variance, or we could even take a point mass distribution. That's the ultimate narrow distribution. It's the distribution which has as a cumulative distribution function a step function. And so to get a kernel density estimate, what we do is if we have a sample of n points, we take n copies of our kernel, we shift each one to be centered at the ith point, and then we average together all of the resulting CDFs, right? So we have let's say 50 copies of the CDF for a very narrow normal distribution, each shifted to have a different mean, and then we average together those 50 CDFs, and we say that that's an estimate of our empirical CDF of the random variable x. So here's an example, right? So the red is again the true, and with a narrow Gaussian kernel, we get the blue line as the empirical estimate, and with a step function kernel, we get this staircase blue line as our estimate. Okay, and so a kernel density estimate has a much simpler expression than the piecewise linear CDF, but it has the disadvantage that we have to choose what distribution we're going to use as our what the kernel is that we're going to use. All right. Okay, so I've given now maybe half a dozen different ways to pick a density function for a continuous random variable. How do we know whether we were right? Right? That seems like an important question. So there's a very useful tool called a QQ plot for checking whether we've got the right family of densities or whether we've got the right density. And so a QQ plot is short for a quantile plot. What it does is it compares two cumulative distribution functions, two CDFs. And in particular, it compares their quantiles. So what is a quantile? A quantile, the alpha quantile of a distribution is the point such that alpha fraction of this time you're going to be below it, right? So just going up to actually all right, well, so let's take, here's an example of a CDF, right? And so let's see. To get the 0.2 quantile, right, what we do is we take the number 0.2 on the y-axis, trace it over until we hit the CDF, and then we look down at the x-axis, right, and that tells us that at approximately 0.24 to 5, something like that, there'll be 20% of the samples will be smaller than that, right? And so that's what a quantile is. The formula for it is just the inverse of the CDF, right? So if we look here, the alpha quantile of a CDF F is just F inverse of alpha. And we'll sometimes as well say percentiles, right? So the 0.2 quantile is the same as the 20th percentile. The 50th percentile is also called the median. That's the 1/2 quantile. All right, and so that's what a quantile is. To make a QQ plot, we just compare the quantiles of two distributions. So we take two CDFs, let's say F hat and F for an empirical CDF and the CDF of a known distribution like a normal, and we want to ask whether the normal distribution is a good match for the observed distribution of our samples. And so what we'll do is we'll vary alpha from 0 to 1 in small increments, let's say 1/50 or 1/100, and compute the alpha quantile of F and the alpha quantile of F hat, and for each one of those alphas, we'll turn that into a point on the QQ plot. So the x-coordinate will be the quantile of, let's say, F, and the y-coordinate will be the alpha quantile of F hat. All right. And so if the two distributions are the same, their quantiles will be approximately the same. If they're the same, they'll be exactly the same, and if they're approximately the same, the quantiles will be approximately the same. And so if our QQ plot shows a straight line of slope 45 degrees going through the origin, then we verify that the two distributions are the same, and if it shows anything else, then we say that there's a difference between the two distributions. So here is an example of a QQ plot. And so what I've done here is that I've taken a normal distribution and the distribution of the mean of 50 coin flips, right? And compared them using a QQ plot. And so the QQ plot is the blue x's. and you can compare them to a straight line of slope 45 degrees going through the origin. That's the red line, and you can see that they're essentially on top of each other. Right, they're not very far apart at all, and so we have verified that these two distributions, they're not the same, because if they were the same, their QQ plot would be actually a straight line, but they're very close because their QQ plot is close to a straight line. So somebody's asking a question about the kernel density estimate. So in this plot, how do you compute the blue line, right? So the formula for the blue line is this, right? So the blue line is f hat, and f hat is the average of n copies of f, where f is our CDF for our kernel, right? Defined right here. And each one of those copies is shifted according to one of our data points. Is it possible for there to be multiple commonly known models that fit the empirical data well? For example, that have straight lines on the QQ plot? Yes, absolutely. There's situations, for example, if we look at this example right here, right? So the blue points actually follow a binomial distribution, right, with probability 0.3 and number of samples equal to 50. And you can see that that binomial distribution is very close to a normal distribution. And so it would be okay to choose either one of those to model our data in this case, because both would be fairly accurate models. And so we would use external considerations to decide which one to choose. For example, the normal could be more analytically tractable, and so we might choose the normal so that we could complete a derivation that lets us check that some algorithm that we're going to use actually works. Or, you know, if we're actually modeling coin flips, we know that the binomial is going to be the truth, and the normal is only going to be an approximation, so we might prefer the truth instead of the approximation. All right, so one nice feature of QQ plots is that they are robust to differences in location and scale. So location means taking your probability density and shifting it left or right, and scale means taking your probability density and stretching it to make it wider or narrower. And so location will change the intercept of a QQ plot. So if you make a QQ plot between a normal of mean 0 and a normal of mean 1, that will just have an intercept that is not equal to the origin. And the same thing with scale. If you scale it, it'll change the slope of the QQ plot, but it'll still be a straight line. So if you make a QQ plot between a normal distribution of standard deviation 1 and a normal distribution of standard deviation 2, you'll get a straight line, but the line will have a slope that's different from 1. You can still use QQ plots if you're looking at a family of distributions that have parameters other than location and scale, but then you would need to estimate those parameters, right, in order to use the QQ plot. So if you want to know, you know, a less common continuous distribution is the gamma distribution, and it has parameters that are not that are neither location nor scale parameters. So if you wanted to know how well a gamma distribution fit your data, what you'd have to do is estimate the parameters of the gamma distribution and then compare the distribution with those estimated parameters to your data. So you could estimate by maximum likelihood, for example. All right, so hopefully everybody remembers maxent from the discrete case. There's an analog of maxent for the continuous case as well. And it mostly proceeds the same way. The only difference is that we get densities instead of probabilities. So we have a random variable capital X, and we define a vector of features t of x, which in our example is going to be x and x squared because that's a good example. But in general, t of x can be any set of functions of x. And then we describe the distribution of x using the mean parameter, which is t bar, the expected value of t of x. And we, given this mean parameter, we define a distribution by saying we're going to pick the one with maximum entropy, subject to the constraint that it has the given vector of moments. Similarly, minimum relative entropy, we can minimize KL divergence to a base distribution P0. And I guess I should mention that for maxent and minimum relative entropy, you can still, right, so just like for a discrete variable, h of x is equal to the sum over little x of minus p of x log p of x. Right. You can have, this is the discrete case. You can have for a continuous random variable, you'll get the integral over all possible values of x of minus p of x log p of x dx, right? And so that's the continuous case, right? And so entropy and similarly KL divergence, basically you just copy the formula and replace sums by integrals, and you take the density then, right? So here in this case, P is a density, not a probability. And you take the density that maximizes entropy or that minimizes KL divergence. And just as in the discrete case, you can get an explicit expression for the maxent distribution or for the minimum relative entropy distribution, and it's the same formula, P0 of x times e to the t of x dot theta minus g of theta. So theta is the natural parameter, g of theta is the normalizing constant, and we choose theta in such a way that we get the desired vector of moments. And this is again called an exponential family. And the formula for g of theta is the same as in the discrete case, except that we replace a sum by an integral. Unlike in the discrete case, for some values of theta, it might actually be impossible to normalize the distribution, and so we just exclude those values of theta. And so normal and beta that we defined above, those are both good examples of exponential families. So the normal distribution uses the vector of statistics that we were talking about, x and x squared. The beta distribution is the one that you get by using log p and log of 1 minus p as our statistics. All right. So I think that we are basically out of time for today. So we'll continue next time talking about power law distributions. And my office hours start now. Feel free to continue asking questions on Piazza. And until next time, I'll talk to you later.